No, he doesn't have to do anything because it does it for him. Anyway, back to this. So, these p-values. When you brought that up, it was interesting. Talking about the first guy, how for your friend, he said he broke his back and he had a heart attack 6 months later, and then he bounced back. It's interesting to hear stuff like that. Your textbook actually has an exercise. I think it was in the last homework section, where it was a study done of people running over age 50. It was a Stanford study. People running over age 50. And they kept track of those who died in the 8-year period of the study. And it was something like 1.5% of a couple thousand people in the study died during the period of the study. And I made a mention of this on the YouTube video that I made for it. They were talking about causes of death or death rates among those who run over age 50. So they were studying folks that are older, that are runners. And I'm assuming they controlled for like the length of run, how far they ran. But they were talking about, causes of death by running, or death by running, 1.5%. And I was concerned about that, because if you're over 50, there are a whole host of other health issues that kick in, of which running might be completely independent. Right? I mean, I'm not saying that running can't kill you. Everybody's heard of Jim, well, maybe you haven't because you're young, but there's a guy named Jim Fix, who was an ultra-marathoner. This is back in the 80s, maybe the early 90s. Dropped dead on a training ride. Had a massive heart attack, dropped dead. This guy was winning marathons. Just dropped dead. I was like, see, you shouldn't run because you can drop dead. One dude had a fluke congenital problem that caused his heart to explode. I think he had one few valve or something like that. But all of a sudden, running becomes bad for you because one person does it. Same thing. Somebody breaks his back and then has a heart attack and is out mountain biking a year later. I'm guessing that's an outlier. Right? I'm guessing that's an outlier, but the problem is the media will jump onto that. I'm not saying your friend is that, but this Jim Fix thing, it made me think of Jim. They jump onto that and people will say you shouldn't run because you're going to have a heart attack. Does one data point undo thousands that support the opposite?
No.
No, it can't, because the margin of error around one data point is essentially infinitely wide. Yes, you were going to say something. Go ahead. I walked right over you. You were saying something.
Oh, no, I was just going to say that it's probably not running, because there can be all kinds of underlying things, and then you go running, and one of them just throws you over the edge.
It's quite possible, and it could be completely independent. Running could exacerbate something, sure,
right,
but it can also be completely independent of that.
Could have got stressed when they his heart exploded.
Of course, there could be something independent. Running may have exacerbated it, but not by itself wouldn't have done anything. Okay, I want to focus on this bad boy right here. What's that capital P mean again, friends? Probability. Probability of what? Probability of what? In this case?
That caffeine lowered heart rate.
Okay, that's the assumption. We're assuming that caffeine wasn't going to lower heart rate, but what happened with the data with submaximal exercise? Let's go together. What happened during submaximal exercise? Submaximal, what happened with caffeine? Heart rate went down. Were we expecting it to?
No.
We went in assuming it wasn't going to, correct? So here it is in words, I think, if I did this right. Yes. Well, here's pictures, I guess. This is a bell curve. We are guaranteed a bell curve by the central limit theorem. Yay. This is one of the reasons we like the central limit theorem. The bell curve is going to show up. What this is called is, this is a sampling distribution. You may remember this phrase from 243. If not, we're going to relearn it right now. A sampling distribution represents all possible data values around a sample statistic, assuming a null hypothesis. So, if you give people caffeine and then make them go participate in a submax workout, there is an average heart rate assuming caffeine isn't doing anything. In other words, it's the same heart rate you would have. It's the same heart rate that you would have if you didn't take caffeine. Remember what we're assuming? Caffeine is not lowering heart rate, which means on average, heart rate is going to be the same whether you're using caffeine or not. It'll be right there. Now, heart rate might vary a little bit this way, a little bit higher than average, but that's within a what? Good! It's within an acceptable number of standard errors, or a margin of error. Good, thank you. Of course, if it gets too high, we are no longer at normal or usual heart rate. We are now at what? But would we be surprised if caffeine put us over here? Would we be surprised if caffeine elevated our heart rate? Probably not, it's caffeine. It's probably going to elevate our heart rate. Or, if at best, not do anything to it. So, here is caffeine has no effect on heart rate. It's exactly the same as those that are not caffeinated. Here the heart rates are going up, but they're still not surprisingly high. Here they're surprisingly high. So that's the elevated bit. Now let's go this way. Let's go this way. Here's average heart rate. What's happening to heart rate now?
Lowering.
It's lowering. Is it surprisingly lowered right now?
No.
No. When does it get surprisingly lowered? Well, that's what I try to indicate with the red little area over there. That red area represents what percentage?
2.5.
Oh, you're thinking two-tailed. Very nice, Cassie. More. It's all in one tail. Cassie said 2.5%. Good for her. She's assuming that there's a red tail here and a red tail here, which add up to 5%. But I put it all in that tail, which means what percent is over there? Perfect. There's your rare event rule. It says, here is what we're expecting to happen with caffeine. Remember, the research hypothesis is caffeine lowers heart rate. The opposite of lower is what? Raise or stay the same. That's what the blue curve is. Raising or staying the same. However, when we got our data back from the experiment, where did our data land? I'll give you a hint. It's the asterisk. The data landed in the region of the curve that's extraordinarily small, less than 5%. That's what that means. It means your data came back and showed a great disagreement with what you were expecting. You were expecting it to land in here somewhere, but it didn't. It landed over here. Holy crap. Holy crap. We were expecting it over there, but instead it landed way over here. What can we imply from this? What can we apply from this? There it is in words. We were assuming, this is exactly what you guys said in words. We were expecting that caffeine would have no effect at all on heart rate during submaximal exercise. That's what we were expecting, that big blue curve. But what happened with our data? The data came back and showed lowered heart rate. So the two halves of that conditional probability, do they agree or disagree? Do they agree? Are they saying the same thing or different things?
Different.
Most definitely different. This one's saying caffeine shouldn't lower heart rate. This one's saying heart rate was lowered. That means they're not agreeing with each other. If they agreed with each other, the probability should be close to what? Or ish. If something agrees wholeheartedly, what do you say to people? I am blank percent in agreement with you. You're getting, well, conversationally, I agree with you 100%. Or something along those lines. I agree with you. The probability should be high if there's agreement. When there's disagreement, the probability should be low. And how low is low enough? You're looking at it behind my head. That's your kickoff. When you get below 5%, you look up at the statement and you say, okay, there are two parts to this statement. One of them is concrete, and one of them was a belief I went into the study holding. Which part is concrete? Which part is unquestionable, assuming that your study was done correct? That you got lowered heart rate data, because you measured that. Unless you screwed up the study or you got an outlier, you got lowered heart rate data. So what's the part that's questionable? The assumption that caffeine doesn't lower heart rate is the questionable. And that's when we put our hands back and we go, what the hell? That's interesting. We were expecting heart rate not to be lowered, but the data came back. The end didn't justify the means, so to speak, right? And the status quo of caffeine didn't lower heart rate appears not to be holding any water. Compare and contrast that with the at-rest and maximal exercise guys that got the placebo and the caffeine. Okay, it's the same curve. It's the same curve. Usual or elevated heart rates. We're giving these guys placebo, we're giving them caffeine at 1.5 milligrams per kilogram, whatever the hell it was. 3 milligrams per kilogram. And we're assuming, in both cases, that caffeine is not going to lower heart rate. And guess what happened in those two cases? It didn't lower heart rate. let me ask you the question a different way. If it was going to lower heart rate, where would these asterisks be? They'd be over here. But where do they land? They landed somewhere over here. I don't know exactly where because I've lost the original study. Give you the link to it. But how can I tell they landed in here? How can I tell they're in here and not here? Good. Dan, look up. Where is it? That tells us it's bigger than 5%. How much bigger? I don't know. Without the raw data or the test statistics, I can't measure. But it's bigger than 5%, which means it's within how many margins of error? Think normal distribution. What are in the tails? Cassie said it earlier. In the tails, you have 2.5%, 2.5%, 5% total. That means how much is in the middle? 95%. Now, if I take the tail that was over here and I put that area here, this is still what? What percent? 5%, which means this is 95%. That's your cutoff again. If the probabilities come back above 5%, it means there was not acceptable disagreement. So in other words, it looks, at least I put this here intentionally, it looks like this asterisk fell in below average. But it wasn't what below average? What word goes in there? Good! It wasn't significantly below average. We allow for the margin of error in the measurement for all kinds of reasons. Sampling error, randomness, all these, actually the same reasons, sampling error and randomness. So you could be a little bit down or a little bit up and still not be off significantly. But when you get too far away from center, then people go, you know what? I don't think it's coincidence anymore. We're so far away from center, the only way it could be coincidence is if we just so happen to grab the outlier. It happened to us, first day of class. Cards, pull the cards out of the deck. Still haven't let you see it. That card's still hidden. But the first thing you guys picked out were 5 black cards. And y'all said, deck is suspect. And I said, how do you know you just didn't pull 5 black cards? And your answer was? Your answer was? That's not an answer. That's the reality. What was your justification for accusing my deck of being rigged?
On average, that isn't going to happen in the first 5 cards.
The first 5 cards, there's a 3% chance of that happening. What's 3% less than? 5%. So in other words, here's the average number of black cards you would see in a deck of cards as you pulled them out. You pulled the first black card, you pulled the first card, it was black. 50-50. Nobody's disagreeing with 50-50. You pull the next black card. Now it's 1 in 4. So what happened? You're not here. You pull the next black card. Now it's 1 in 8. You pull the next black card. Now it's 1 in 16. And Rachel had already given up. She's like, the hell with this, it's rigged. But then you pull the 5th black card, and now you're here. And that's when you sit back and you go, okay, roll, USOB, something's up, show me the deck. And I say no. I say no because it's your population. But you don't need to see the population to know it's most likely not a fair deck based on that result. Fair? Yes? Maybe. Alright? Here this is, back to the caffeine. Here it is in words. Not at rest. That's what the conditional probability would look like. Now you guys are seeing this is just slides on the handout, right? Just going through it, yeah. What's the chance we got non-lowered heart rate data? Assuming that caffeine does not lower? Well, what do you think? Does this piece disagree with that piece?
No.
No! One says caffeine isn't going to lower, the other says that caffeine didn't lower. So it's perfect agreement. How can you tell there's perfect agreement without even seeing the graph? Numerically? Careful, that's bigger than 5%. That's greater than 5%. 5% is less than that, which means that's greater than 5%. Thank you, Dina. That's the one thing that screws 244 students up more than anything, is interpreting that sign going the right way. And I don't know the best way to do it. Nobody say alligator, that pisses me off. Just get comfortable with the greater than less than sign. Just realize. P greater than 5. That means the probability came in larger than 5%. Fair enough? Same thing happened with maximal exercise. There's maximal. Now, it's wordy It's fairly wordy because these experiments generally are done in very, very specific areas with very, very specific conditions. So you've got caffeine, but not only do you have caffeine, you've got this maximal exercise versus being at rest. So break it down into larger, more general areas. Caffeine had no lowering effect on heart rate. Caffeine had no lowering effect on heart rate. Okay, we were expecting that during maximal exercise. And guess what happened during maximal exercise? The heart rates came back unlowered. Is that a disagreement? That's a perfect agreement. So this agrees with this, and we can tell by that. Now here's the thing. When you read research articles, you're not going to see all this. You're going to read this that's now grayed out. That's what you're going to see. You're going to see this constantly. This whole section is about interpreting those and making sure you know what they're telling you and what the hell they might be wrong. We'll come back to that momentarily. And when I say momentarily, I might be next Tuesday. Here is the takeaway so far. Big p-values mean agreement in the two halves of your conditional probability. The two pieces, the part that you know happened, which is the data, the part that you know happened, which is the data, and the part that you assumed was going to happen, which is your null hypothesis. That means the two pieces agree. The two pieces agree with each other, or are congruent to each other, or in some way imply the fact that they're not disagreeing with each other. Which I guess the best word for that, not disagreeing, would be agree. So unfortunately for the researcher, if they really want something to happen, it means whatever you're studying had no effect. So if you were studying to see if caffeine lowers heart rate at rest or during maximal exercise, and you get your data back and you go, oh well, it doesn't, you're going to get a big p-value. This is a little bit counterintuitive, isn't it? Because you might think to yourself, if there's no agreement, we should have a small p-value. The more agreement, you should see, but you got to remember what you're agreeing with. You're agreeing with the null hypothesis. So when you have a large p-value, you get great agreement with the null. The null is the opposite that you want to prove. Is everybody pissed off about that yet? That we're assuming the opposite? Who's pissed? Yeah, we pissed about that? We're not pissed about that. You're okay with that? Who's not sure if they're okay with it or not? Okay, good. I like that. We're not sure. We're okay with it because I'm saying it. That's the worst reason. Here's why. Here's why. If I may, I'm going to back up and come back to this. Remember this curve? This beautiful blue curve right here? This beautiful blue curve. How do we know the shape of this curve? How do we know the shape of this curve? How do we know? How do you think we know it? I know that usual heart rates average right here. And they have a plus or minus. How do I know all this stuff? Am I clairvoyant? How do I know this? What do you think? Give me some ideas.
Like previous studies?
Previous studies, Laura, I love that. We've done previous studies. We have years of data from previous studies showing us what a baseline heart rate is. This happens all the time. Anytime you want to compare the effects of exercise or anything else on heart rate, you have to start from a baseline. We've got years of studies, previous studies, that have baseline heart rates. And since we have years of studies with different sampling sizes with baseline heart rates, not only do we have that, we also have margins of error around it because we have multiple studies, we have standard deviations. What don't we have? We don't have a curve like that for elite male cyclists who drink caffeine and then go out and do maximal exercise. In other words, I have no freaking idea what that curve looks like. Yet, until I do the study. But because I don't have a comparative curve yet, it's much easier for me to compare my data point that I got from my experiment to a curve I already know exists and see if it sits on it or not. If it sits on it, then I claim, well, caffeine's no different than not having caffeine. But if it gets down here, then I can say, oh, maybe I have my own curve. Maybe I've got my own curve now. We'll get into that momentarily. But that's why we test against the null. The null is known, at least with an experimental error. I say known with quotes. The null is known. The null is essentially, if you will, a parametric study. in that we've already tracked the parameter 95% of the time using confidence intervals from previous studies. If we trust those studies, if they've been shown reliable, let's keep using that to baseline off of. Is that fair? Or is it just Thursday and you're kind of like, okay, that's honest? Yeah, okay, let's be honest. But that's the reason. The reason is sheer convenience, friends. We already have this curve. It's easier to test against a curve we already have than to test and create a new one that's got too much uncertainty. If you've got reliability in studies already, hell, use that one. Okay, let's get back to this, the big idea. Here was the first big idea, big p-values. If you're a researcher trying to prove something and you get a big p-value, how do you feel? If you're trying to prove something, you really, really want it to work and you want to write it up and publish it and get famous, and you get a big p-value, how do you feel? You feel pretty bad, because that means your research study didn't prove anything interesting. A big p-value means whatever you were studying agrees with whatever everybody else has already seen, which means you saw nothing new. Now, this is not necessarily a bad thing. If you were expecting to see something terrible, maybe this just agrees with the fact that 95% of the time it's not going to be terrible. But the fact of the matter is, if you're trying to show a contradiction, a big p-value is not it. And these are the ones you don't often read about in papers, because they don't show anything. You notice our study has 3 p-values: at rest, submax, and maximal exercise. 2 of the 3 of those showed nothing. But the title of the article didn't have the words at rest or maximal. It had submaximal. That's what the article was all about. And that comes to the big idea, part of the second. Oh, excuse me. Here we go. We're still at big p-values. Yeah, time out. We'll go back to large p-values. I forgot I put this in here. Large p-values imply that your data fall within good 95% confidence, which is kind of down here. Large p-values are generally those greater than 0.05 or 5%. I was looking for a more general way of phrasing it would be within 2 standard deviations. 2 standard deviations, if that makes sense. Now, you have to identify in your mind the elasticity of the phrase 2 standard deviations. Now, why do I say that? I'm going to back up. Where are 2 standard deviations here? Where are 2 standard deviations here? And this goes back to what Cassie said earlier. Go ahead, where are 2 standard deviations?
It's all of them, right?
You got it, Will. It's an asymmetric 2 standard deviations. Here's your average, but now you've got this all the way out to negative or positive infinity. So you have to kind of flex your mind a little bit around the idea of what a standard deviation looks like. Sometimes it's what's called two-tailed, which is what Cassie said. We're going to get into lots of those, I promise. But lots of times, if you're trying to say something increased or decreased, it becomes a one-tailed, asymmetric 2 standard deviations. That's why I like thinking about it in terms of percentages rather than standard deviations. It's 95%. If we land within 95%, we haven't changed. If we land outside of 95%, i.e. in that 5% or less, something has changed. And that's the point here, this last little line. There. Large p-values, and I put it in quotes. I put it in quotes because large only means greater than 5%. It only means greater than 5%. To which students will often ask, well, what if it's only 5.5%? That's true. What's only 5.5%? What if it is only 5.5%? What if it's only 6%? What if it's 5.01%? That's bigger than 5%, right? That sneaks in using the law of large number, or the rare event rule. We'll deal with that in turn as we go through the course, I promise you. I promise you. Because when that happens, there's no statistical answer, but there is a great research answer when it gets to. And we'll get to that as we go, I promise. Cool so far? How about small ones? How about small ones? Small p-values. These are the ones that sneak in under 5%. Less than 5% means the 2 pieces of your conditional probability do what to each other?
Disagree.
They disagree with each other. You're expecting something, and the opposite happens. You're expecting caffeine to not lower heart rate sub-max, and holy crap, it lowered it sub-max. Well, that's interesting. That's interesting. 2 explanations for that. One is that you got deviant data. It's a bell curve. And you just happen to end up out there in the tail. Which is what I was trying to tell you guys on the first day of class when you got all pissed at me. Your deck is rigged. You don't know that for certain. You pulled 5 black cards out. There is a chance of that happening. To which you retorted. There's a less than 5% chance that it happening, which means we should or shouldn't have seen it happen. We should not have seen it happen, but we did. That's a contradiction. We shouldn't have seen it happen, but we did. That's a contradiction. That means no agreement between this and this, which means the probability comes in under 5%, which means we are no longer within those 2 standard deviations. We are no longer within those 2 standard deviations. We are now popped outside of 2 standard deviations. There's your rare event rule. Outside of 2 standard deviations means whatever you saw, you shouldn't have seen. On average. Now, granted, there are outliers and outliers exist. But even though they exist, you shouldn't see them. And you definitely shouldn't see them on the first shot, as we've seen over and over and over again. If you do this study 100 times, I would expect 5 studies to have outliers. However, I would not expect 1 out of 1 to have outliers. Which means I most likely didn't see an outlier. I most likely saw something close to average. And if average meant lowered heart rate, maybe we have a new average to talk about. That's the point. That's the point. With me so far? Any questions you have at this moment? At this moment. Okay. Check out the next article, which is about green tea and breast cancer rates. Let's extract some more good information from this.
What is 18.7 per 100,000 woman years?
18.7 per 100,000 or per 1,000 woman years. It sounds like they've got a new normalized way of measuring time rather than woman years. And I guess what they're doing is they're allowing for older and younger women to be included in the same study. So you can't just use
So they're just taking a bunch of women, adding them to years.
It's a weighted average, exactly. The 18.7 per whatever is a weighted average, allowing for the fact that an older woman is more likely to have cancer overall, just because she's been alive longer. Does that make sense, Chris? So it's a weighted average is all it is. It's one of those units like kilogram meters per second squared that you're really like, what the hell is this? And then you have to have that unit to weight it properly. Fair enough? Good question, my friend. Ooh, let's shut the camera down too. Listen to the sounds of you guys reading.